Okay, so let us continue with fundamentals of combustion. Today's lecture will be on first law and second law of thermodynamics applied to combustion problems. So here we will try to calculate the heat released by the combustion process, then the temperature attained by the combustion chamber, and the composition of the products in equilibrium based upon a given temperature and pressure. Okay, so first law of thermodynamics is applied to calculate the heat released from a combustion reaction. Okay, so combustion is an oxidation reaction which is exothermic in nature. So heat is released, heat is generated, and that is transferred to the surroundings, and the first law is used based upon what is the problem under hand. So it is used and the heat released is calculated. So heat is released from the combustion reaction due to differences in the energy levels of the reactants and the products. Okay, so you can say energy or enthalpy in the reactants and products. Okay, so heat is released because the reactants, okay, are at higher energy level than the products. So the difference in the energy comes out as heat. So we have already seen this. Okay, so now, so let us consider a system. System is a space under consideration in which there will be energy transfers. Okay, work transfer, heat transfer, etc. are allowed, but there is no mass transfer which is taking place. So initially you fill up the reactants in that, and upon ignition products are formed. Okay, so no other mass transfer is allowed. So that is the system. Say we can say closed system, and this system initially has reactants. So that reactant state is defined as state 1. So once ignition is accomplished, then reaction occurs, the chemical reaction occurs, and products are formed. So the products when completely formed, that state is called state 2. Okay, now the first law can be applied to this state. We have already seen that this is a highly irreversible process. Okay, once the reactants are converted into products, the reverse reaction is not possible, and you give sufficient time for the reaction to occur, as we do in thermodynamics. After the completion of reaction, you get the state 2 where only products are present. Okay, what is the composition of product, etc. we will see based upon what is the temperature prevailing in the combustion chamber or the system. We will be able to calculate it using these laws. We will see that later. So now if you apply the first law of thermodynamics between these two states, so initial state is state 1 reactant state, final state is state 2 the product state, so 1 to 2. So during this process, what is the heat interaction between the system and the surrounding, that is labeled as Q12. Q12 is the heat interaction between the system and the surrounding when this change of state from 1 to 2 occurs. Similarly, there may be some work interaction. So that is defined as W1 to 2. Okay. So in the absence of changes in the kinetic energy and potential energies, the only energy change what we see is the change in the internal energy U2 minus U1. So the first law of thermodynamics for this system is written as the difference between the heat interaction and the work interaction is equal to the change in the internal energy of the system. So in the if there is a change in kinetic energy or potential energy, that may also be added here. So let us in many cases it is the changes in kinetic energy and potential energy are negligible. So we neglect that, so that we can write the first law as stated here. Okay, so this is the first law of the system. Okay, here U is internal energy, and the Q1 to 2 is the heat interaction during the change of state, and W1 to 2 is the corresponding work interaction when the change of state occurs. Okay, now let us consider two cases. One is the pressure of the system is held constant. So if the pressure of the system is constant, so constant pressure process. Okay, then we will again consider, like for example, consider a piston cylinder arrangement. In a cylinder there is a piston, so which is almost frictionless and it is free to move. So based upon the pressure rise here inside the system, the piston can move up gradually. So, if you take this device, the pressure is held constant because of the movement of the piston, and this you can operate this at any pressure based upon whatever load you have in the external loads, etc. If you have, you can operate this device under any pressure. So, let us keep the pressure constant, say P, and when you have this ideal gas mixture which is going to be there. So, initially the reactants are ideal gas mixtures, then products are formed. They are simple compressible substances. Okay, so mixture of ideal gases, they are simple compressible substances, and they are present in the cylinder. So, this movement of the piston in the cylinder contributes to what is called a displacement work. So, normally it is given by P times dV, integral P dV. So, now see, since pressure is a constant, we can write the work interaction, the displacement work which is involved in the constant pressure process like a piston cylinder device is P into delta V. Delta V is the change in the volume, V2 minus V1. So, this is V2 minus V1. So, the piston goes up from a volume of V1 and it occupies, the gases now occupy in the second state the volume V2. Pressure is constant. Okay. So, now if you write the, so incorporate this in the first law and write this, you can say that the heat interaction will be equal to the change in internal energy plus. So, here please note that P2 V2 minus P1 V1 is written here, but actually this is nothing but P times V2 minus V1. So, in other words, P2 equal to P1 equal to P. So, constant pressure process. So, I can write this. So, why I am doing this here, because I am going to club U2 plus P2 V2 and U1 plus P1 V1, and as per the definition they are the enthalpies. So, U2 plus P2 V2 will be H2 and U1 plus P1 V1 will be H1. So, H2 minus H1, that is the final state enthalpy minus initial state enthalpy. So, which is nothing but the enthalpy of the product mixture minus the enthalpy of the reactant mixture. So, that will be the heat interaction. The heat interaction in the system will be the enthalpy of the product mixture minus enthalpy of the reactant mixture if the combustion occurs during a constant pressure process. Okay. On the other hand, if the process is constant volume, so like in a bomb calorimeter, okay, you have a constant volume, rigid vessel, and you allow the pressure to rise. Okay, now what happens is, since the volume does not change, delta V equal to 0, that means the displacement work will be equal to 0. W12 will be P into delta V, so the delta V equal to 0. So, P dV, so the dV is equal to 0, so W122 will be equal to 0. So, in this scenario, you get the heat interaction Q122 as the change in the internal energy U2, the final state internal energy, minus U1, the initial state internal energy, or the product's internal energy minus the reactant's internal energy. So, this is the, so for a system undergoing a constant pressure process, the change in the enthalpy will be the heat interaction. So, Q122 will be equal to Hp minus Hr. For the constant volume process, the heat interaction will be the change in the internal energy. So, Q122 will be equal to Up minus Ur. So, this is the first law applied to a system. Now, let us expand this more. Consider the constant volume process. We have arrived that the heat interaction will be equal to U2 minus U1, okay, or Up minus Ur. Now, generally we do not, it is not easy to measure internal energies. So, when you want to measure, it is easy to measure the enthalpy of the species, individual species and so on. So, normally it is easy to calculate the enthalpy of the mixture, product mixture or reactant mixture. Okay. So, normally they are tabulated in say in NIST website and so on. So, the enthalpy tables are available, but internal energies are calculated based upon the definition of the enthalpy. Okay. So, in this case, for example, Hp, the product's enthalpy can be written as Up plus pressure of the product into the volume. Volume is constant, this constant pressure, constant volume process. Okay, so constant volume process, the volume is constant, so I can write this. So now, based upon this, we can also write UP plus this PV can be written as NR, the equation of state for the ideal gas. So, okay, so number of moles of the product mixture into universal gas constant RU times Tp. So, this you can write. So, now UP can be calculated as HP minus NP RU Tp. So, that is what we have written here. So, in terms of enthalpy and using the equation of state, we calculate the internal energy of the product mixture. So, you have to first calculate the enthalpy of the product mixture, then use the equation of state, subtract that to that, so that you get the internal energy of the product mixture. Similarly, you do it for the reactants, and this difference is the heat energy. Normally, we use enthalpy. So, this means that the enthalpy is very important for us, enthalpy of the calculating enthalpy of the mixture. So, how to calculate that? That is the important thing which we will see later. Okay, now here as I told you, NP and NR are the number of moles of the products and reactants in kilomole, and HP is the enthalpy of the product mixture, and HR is that of the reactant mixture. TP and TR are the temperatures of the product and reactants. Okay, so this is the way right for the system. Now, if you take see, several reactors are not system based, they are flow process. Flow, you inject the reactants and products come out. Okay, so for example, I can inject the reactor in a furnace and the product comes out as the exhaust gas. Okay, so after going through the boilers and so on. So this means that we will consider a control. We have to consider a control volume. Okay. In this control volume, mostly after initial transient operation, time dependent operation, mostly this process will be continuously steady state. Okay, so normally continuously feed reactants and products come out, and the variations are not much with time. So it's almost a steady state, steady flow process. So let us consider such a steady flow process. Okay, now we need a control volume for this. So what happens here is the reactor mixture flows through the reactor, which is a control volume. So for example, I have a control volume like this, and the reactor mixture flows through here, flows through this. Then combustion occurs here in this reactor. So this is reactor. So this is the control volume. So reactant comes in, and whatever heat is generated, we can take it out. So heat interaction is allowed here. Similarly, products goes out. Products go out. So here you can see that heat interaction is allowed. Similarly, you can also have some work interaction like stirring work and so on. So basically, we don't have in a combustion chamber. Nobody stirs a combustion chamber. So if you see this, you have heat interaction. So actually, heat which is released during the chemical reaction will be absorbed by the surroundings. So heat is transferred to the surroundings, reactants enter, reaction takes place, heat is transferred to surroundings, products leave. So this is a control volume here. This is a control volume in which we are trying to apply the first law. So what is this Q dot? That is what we are trying to find now. So now this is a steady process. So initially when you start the reactor, it may be time dependent. Okay, for example, the reactor is going to run for say some few months. Initially for some few hours, it may be time dependent in nature. After that, slowly it will become a steady state. So we will be able to supply the required fuel flow rate, air flow rate. So the reactants are fed at a given velocities and mass flow rates. Then products are formed, they come out with the whatever temperature you want based upon the heat interaction what you do with the reactor. Okay, so for a steady state, steady flow process, when reactant mixture flows through a reactor and product flows out of the reactor, the heat interaction, now I am not considering any work interaction, heat interaction in the absence of any other work. Okay, so normally there is no displacement work here, volume is constant, so no displacement work is considered, but we can have some other type of work, extrusion work and electrical work, etc., but not suitable for this particular reactor. So we don't normally use that. So we have to use what is called the first law of control volume to determine Q dot. Okay, so here I have let this dots etc. I have not put here for convenience. Okay, because I have written here what is the nomenclature below this equation. So, I have not put dots. Normally it is better to put dots here, or you can understand like this. So, the rate at which heat is released. So, when you want to say rate at which a particular quantity is transferred, then it is customary to put a overhead dot like this. Okay, here you can see that a certain number of moles of product mixture flow out at a given rate. So, NP is the number of moles of the product mixture. So, NP dot means number of moles which is going out per unit time. So, that is NP dot. Similarly, NR dot is the number of moles of the reactants which are coming in at a particular rate, time dependent rate. So, actually this is steady. So, the number of, please understand that here the rate at which number of moles of product leave the combustor is not equal to the rate at which the number of moles of reactant enter, but mass is same. The mass of the reactants entering the combustion chamber will be same as the mass of the product which are leaving. In fact, mass of the fuel plus mass of the oxidizer will be equal to mass of the, so mass is conserved, mass of the product. So, mass is conserved, but the number of moles need not be conserved. So, we have to write this in this way. So, now we can see that the first law of control volume states that the rate at which heat interaction occur. So, I have written here Q, I have not put dot, but anyway you can put dot also if you want. So, the Q dot is the rate at which heat interaction occurs between the control volume and the surroundings. Okay, or reactor, the control volume is the reactor or combustion chamber and the surroundings, and NP is the rate at which number of moles of the products which is leave. So, again I can put the dot here. So, I have not put it just for convenience. Okay, now similarly the N dot R is the rate at which the number of moles of reactants which is enter the control volume. Now, again one more nomenclature is, if you say see turns etc., for molar specific quantities, molar specific enthalpy. So, HP is the molar specific enthalpy of the product species, that is normally you put a overhead bar. Here also you can put a overhead bar. When you put a overhead bar, I emphasize the fact that this is a molar based quantity. So, if I say H, this is H by M, which is joule per kg. When I say H bar, this is H by N, which is joule per kilomole. So, for convenience again I have not put the overhead bar or overhead dot for representing the molar specific volume or molar specific quantity or the rate. Okay, anyway you can just remember this nomenclature. So, HP is in molar specific enthalpy of the product species, and HR is the molar specific enthalpy of the reactant species. Now, you can see, for example, we will write the equation, and we have already seen how to do this. So, for example, if there is 1 mole of methane and say 2 moles of oxygen, then reactant species is 1 into H of CH4 plus 2 into H of O2. So, that summation is done here to get the mixture's enthalpy. Similarly, for product CO2, H2O, nitrogen may be present. So, based upon number of moles of each, you have to multiply the number of moles that times the enthalpy, its enthalpy. So, species enthalpy should be multiplied to get the product enthalpy reactant. So, in summary, this is nothing but product enthalpy minus reactant enthalpy, because this flow process is normally a constant pressure process. So, we have already seen here, for a constant pressure process, Q12 heat interaction in a system, for example, Q12 is HP minus HR, the change in the enthalpy of the system, that is HP, the final state enthalpy, minus HR, the initial state enthalpy. Similar to that, for a steady flow process, you see that this is the product enthalpy. Okay, this is product enthalpy, okay, and this is the reactant enthalpy. So, the rate at which the heat is released from the combustion chamber or the reactor will be equal to the rate at which the enthalpy of the product leave and rate at which the enthalpy of the reactants enter. So, that is the difference here. So, but the point I want to emphasize here is, in a steady state, the steady flow process is also a constant pressure, but pressure remains almost a constant, not much variation will be found. Any flow process will be having, we will behave like a constant pressure process, pressure will not change much, small changes may be there. Okay. So, this is the first law application. So, to just quickly recollect, first law for a system, there is no mass transfer allowed here, is written in simple terms. The heat interaction will be equal to Hp minus Hr if the process is constant pressure process, or the heat interaction is written as Up minus Ur, change in internal energy, if this is a constant volume process. And you have to keep in mind that the internal energies are written in terms of enthalpies and the equation of states. Okay. For a steady flow process, the rate at which the reactant enter and rate at which the number of moles of product leave, etc. are taken into consideration, and the rate at which heat transfer occurs is calculated using this simple equation. So for all this we require enthalpy values. So normally we go for molar specific enthalpy values H for each species and try to find the mixtures values. Okay. Now heat calculation, since the enthalpy of the product mixture is lower than that of the reactant mixture, the heat interaction between the system or the control volume, now we can say system or control volume whatever, and the surroundings is negative. Okay. So this means what? So the heat interaction is negative means the heat is transferred out of the system or out of the control volume by the sign convention of heat. Heat transferred to a system or heat transferred to a control volume is considered positive. On the other hand, if heat is rejected by the system or control volume, it is taken as negative. So by this convention, okay, so it's called like a heat engine convention. For the heat engine, the heat given to the heat engine is positive and heat rejected by the heat engine is negative. Okay, so the difference between these two is the work. So by the heat engine convention, we will see that the heat interaction in a system or control volume is actually negative because the heat is rejected by this reactor to the surroundings. Okay, so this change is called heat of reaction. We represent that by delta H suffix R. Okay, so delta HR is the heat of reaction. Okay, so now we will say delta HR will be equal to Hp minus Hr for constant pressure system. Okay, similarly I can write delta HR equal to Up minus Ur for constant volume system. Okay, so delta HR is the heat of the reaction. So since Hp is lesser than Hr or Up is lesser than Ur, you get delta Hr as a negative quantity, implying that the heat is rejected from the system or control volume to the surroundings. For the surroundings, the heat received by the surroundings, that is positive. So for the surroundings, taking surrounding as a system now, you will see that the heat interaction is positive. Okay, so surrounding now can be taken as a control volume of system. Okay, and that is positive now. So this heat which is received by the surrounding is called heat of combustion. So that is delta Hc. So now we can say that delta Hc is equal to minus of delta Hr. Okay, so this is the, so again some definitions here. So by applying the first law, we will be able to calculate the heat of reaction. Heat of reaction is delta Hr. So based upon the state, final state, the product state, we will calculate the enthalpy or internal energy of the product mixture by calculating the enthalpies of the individual species in the product and applying chain rule or mixing rule, what we say, we calculate the enthalpy of the product mixture. Similarly, calculate the enthalpy of the reactor mixture and calculate delta Hr. Okay. Now, let us consider, so normally we have to have some reference state. Please understand that all these properties we have to have some reference state. So the reference state is actually two properties are required to fix this. One is pressure, another is temperature. So the temperature basically is taken as 25 degrees centigrade, the atmospheric temperature. Okay, ambient temperature 298 Kelvin, 25 degrees centigrade, 298 Kelvin. That is taken as the reference temperature, and reference pressure is 1 atmosphere, atmospheric pressure, 1 atmosphere is the reference pressure. But enthalpy or internal energy does not depend on the pressure, so it is better to only refer the temperature here. So let the reactants be at a temperature of 298 Kelvin, which is reference temperature. Reaction occurs and products are formed, and you try to once the products are completely formed, then you try to extract heat so that the products cool, and they also reach temperature of 298 Kelvin. So you cool the products until the products reach the temperature of 298 Kelvin. So reactants enter, or reactants are initially present at 298 Kelvin. Reaction occurs, then finally the heat is extracted such that the products are going to be cooled and the products reach the reference state of 298 Kelvin. Okay. In this scenario, the heat released, okay, or the heat of reaction is called standard heat of reaction, because we are operating in the standard state. Initially reactants are standard state, finally reactants are standard state. So you will be able to extract whatever heat is possible. That heat of reaction is this. See, please understand that the heat of reaction is not a constant because of the variation in temperature. For example, reactants can come in at any temperature. I can preheat air and supply with fuel, okay, or for example I can heat the liquid fuel to some temperature and supply the hot liquid fuel, or vaporize that under hot condition and supply the vapors, hot vapors. So reactants may not enter at 298 Kelvin, they can enter at any temperature. Similarly, I need not completely cool it. See, there is a danger of cooling it completely because the reaction may not fully complete. So if I do that, instead of coming out at 298 Kelvin, the products can come out say at 500 Kelvin, something like that. So in such scenarios, the heat of reaction can be varying because of the conditions. The enthalpy is calculated at a particular temperature for each species, and the mixing rule is used to find the reactant or product mixtures enthalpy, and it is used in delta HR calculation. Okay, but when I say standard heat of reaction, I actually do the calculation. It may not occur, it may not be possible to do this, but we can actually extract data and get this based upon the property evaluation. I can calculate what is the amount of heat that can be extracted such that reactants are at 298 Kelvin, products formed are also cooled to 298 Kelvin. So that will give me the maximum heat which can be extracted, because the atmospheric condition is 298 Kelvin, let us say. I cannot cool it beyond 298 Kelvin, so it is not worth it to cool below the atmospheric temperature. So what I emphasize here is the standard heat of reaction is the heat which is extracted until the products are cooled to 298 Kelvin, which is the maximum value what we get. So this standard heat of reaction is called the calorific value. Okay, so this is expressed in per kilomole or per kg of fuel, basically whatever we want you can express this. So you can see that this calorific value, or this is also called a heating value. Okay, under a particular reference condition or a standard condition, if this experiment is done and the heat interaction is calculated, then you get the calorific value or heating value, which is called standard heat of reaction. Basically the calorific value or heating value are negative of standard heat of reaction, it is the heat of combustion. So you can say standard heat of combustion is called calorific value or heating value, okay, because that should be positive. So heat of reaction is negative, standard heat of reaction also is negative basically. Okay, now this is one definition what we want. So this will be a important property for a particular fuel. What is standard heat of reaction? That is calorific value. That is very important property, as we have already seen. Now the products, when you have a hydrocarbon or hydrogen, when you burn the hydrogen, water vapor is produced. So based upon the temperature, when you try to cool it, for example, when you try to extract heat, it is the temperature is going to be reduced. So when you go to say 298 Kelvin, what happens is the product which has water vapor, some of the water may condense to liquid. Okay, so that means that we have two scenarios now. If none of the water is going to be condensed, or if all the water condenses, what will be the heat of reaction. So, standard heat of reaction, again I am trying to cool it to 298 Kelvin, cool the product to 298 Kelvin, supplying reactants at 298 Kelvin. Now, product mixture, water vapor, say what happens is basically it is a mixture, okay. So, we know definitely that 100 is the boiling point of the water, but if you have a partial pressure of the water, see if that is for the pure water, okay. Now, if you have water vapor, for example, water vapor is only having some mole fraction along with the product it is existing. So, based upon the partial pressure of the water vapor, okay, a dew point temperature may occur when you steadily cool it. A dew point temperature may come. After it reaches this dew point temperature, the water condenses basically. So, the two scenarios you can see. One scenario we can assume all the water to be in vapor state, or we can assume that all the water has condensed to a liquid state.